All right, so we are entering chapter 4, okay, and we've been building up this hierarchy, right? We kind of went in a weird order, to be honest. We kind of started with assembly, and then we kind of jumped down to digital logic. But if you think about it, right, we have this hierarchy we've been talking about over and over again. Get my slides in sync here. All right, and it looks a little something like this. Right, so we've got these high-level languages, right, that we write code in, C++, Python, Java, JavaScript, whatever it is, right? And more or less, we say that these languages get compiled into assembly language. And yes, I'm repeating myself for probably the 100th time this semester. Hopefully, if there's nothing else you take away from this course, it's this hierarchy right here, right? We compile that down into assembly language. We looked at the MIPS assembly language in particular, okay? But it doesn't really matter. Right, it's like when you learn a new language, right? Everyone argues about what should be your first language in your intro programming courses. I think it's C++ here. At my last place, it was Java. Some schools, they do Python, and they swear by that's the only way that you can do it, right? Who cares is what I say, right? I mean, I care, but only to the extent of the course should be an intro to computer science, not an intro to Java or an intro to Python, right? What we're teaching you is essentially, or what you should be learning in one of those classes is the fundamentals of programming, right? You just so happen to do it in one particular language. Now, I think there is strategy for what languages, we might teach in an intro course, because it can be easier to jump from one language to another. I think it could be easier to jump from C++ to Python versus the other way around, because C++ is a little harder, right? So if you learn the harder first, easier to jump to the easier language. All that to say, we looked at MIPS. Okay, don't get caught up in MIPS. That's just one particular assembly language. I've taught x86 before. It's a lot harder. Okay, it just is what it is. There's uses for both of them. Okay, so we looked at MIPS. Okay, and then we said that MIPS, or that assembly language, it kind of goes hand in hand with the operating system. Okay, but ultimately that assembly and the operating system, the layers below that are the ISA, the instruction set architecture. We said that is the set of instructions that a processor is guaranteed to be able to execute. Okay, it's just a specification more than anything. Okay, and with that ISA, we have microarchitectures below that. Okay, and that's kind of the big question mark that we haven't really talked about, is what is a microarchitecture? What we then did is we actually kind of talked about assembly and ISA, and then we skipped right down here to transistor and digital logic. All right, so we kind of know what digital logic is and transistors, and that digital logic's Boolean gates and the transistors are just the building blocks of the Boolean gates, right? And then we said at the very, very bottom level, we have like that chemical atomic level. Okay, so we're going to focus here in this chapter on this transition, the instruction set architecture to microarchitecture. So you're going to see a lot of kind of like assembly, ISA intermixed with microarchitecture here, okay, because they kind of go hand in hand. That's the interface that we're at right now. You're not going to see anything that have to do with high-level languages or transistors, right, because that's kind of buried down a level below. Okay, so what we mean, right, is we talked about the ISA is really just a document. It's a document that says, hey, any processor that implements the MIPS ISA will have an add I instruction. Okay, something like that, right? And it will have this many arguments or this many operands. But how do I actually implement that in digital logic? Okay, well, that's where the microarchitecture comes through. Okay, and you'll start to see graphs that look a little bit like this, and we're going to kind of focus in on one particular microarchitecture today. And then obviously we know that well, I don't know if it's obvious or not, but we've at least mentioned it before, that elements of that microarchitecture. So we kind of had this image right here. This is a kind of a classic symbol for an ALU. Okay, so this ALU is broken down into something like this, into digital logic. We actually have our own ALU slice that we've been working with, which we'll bring back up again. Okay, so anyway, just wanted to kind of point out this picture again before we jump into this chapter, because this is what we're talking about. Okay, we're talking about the organization of a processor at this level. And this is what I would call the data path. It's basically how data flows through your processor through the like what are the core components that data is flowing through when you want to execute an instruction. Okay, I want to add two registers together. Well, how am I getting the data out of those registers into the ALU to actually do the addition? And then how am I getting the data out of that ALU and back into a third register to save it, or maybe save it back into one of the ones you sourced it from. Okay, so the data path is really what we're going to focus on. This is a key idea of computer architecture. Okay, so there's really no such thing as a generic microarchitecture. Okay, so what we'll find is that every microarchitecture, every ISA is really kind of a special case. There will be some similarities that we can draw from architecture to architecture, and I'm going to kind of focus in on that a little bit. So all that to say, there's a number of different things. Just like we said, there's a number of different languages you could do as your first language in an intro programming course, and it kind of matters. It kind of doesn't, right? The same is true here. There's a number of different microarchitectures we could choose from. Okay, we're going to choose one that's actually not covered in the particular Xi book. So I'm gonna pull from the Xi book a little bit later as a comparison. But I'm actually going to, so this is like a little image of the Xi book data path, which you may be seen by this point. I'm not sure what part it is in the Xi book reading. We're actually going to focus on something I've taught before and had good luck teaching, and I think it's fairly straightforward. It's simpler in some ways, and so I think it'll be a good starting point to kind of look at processor data paths. In some ways it goes a little bit more detailed, in some ways it's not as detailed, but so what I want to do is I'm going to focus on this. This is called the IJVM, the Integer Java Virtual Machine. Okay, and it's basically like a kind of a software version of a data path. This is basically what like the Java Virtual Machine is doing, right? Remember, Java Virtual Machine, it's like an emulated processor is actually what it is, and it runs this Java bytecode. This thing is what, or at least some version of this is probably a simple version of it, and maybe even an old one. But this is like the simulate. This is how Java can be executed on multiple machines, is because it has something like this little fake processor that is executing the Java bytecode. Okay. So anyway, so we're going to kind of take a look at this particular microarchitecture, and then later on, probably not today, but then maybe on Thursday, we'll see. I might try to at least pull back some of the imagery that you've probably seen before in the Xi book relating to the data path, and maybe make some parallels there. So I think it's even more valuable to look at two different microarchitectures, so you can kind of see some of the trade-offs, and you can also see what we'll begin to see is how the microarchitecture really ties in hand with the assembly. And we'll see how, based on how the assembly language works, you'll see very clearly how that will actually impact your microarchitecture and how complex it is or how simple it is in certain areas. And that's really what it's all about, right? Is as a processor designer, you're making all these trade-offs, and you're saying, hey, this would be easier here, but it's probably going to make things harder somewhere else, right? This design decision, right? There's always these trade-offs. And so hopefully we'll begin to kind of see some of those as we look at one or two of these microarchitectures. Okay. So anyway, these next few slides you have seen before, I believe is like chapter 1 or 2. But we are going to kind of look at, and one thing I like about, I mean, this is all pretty much the same, both these microarchitectures, both the IJVM and the MIPS microarchitecture. But the data path of a typical von Neumann machine, this is what we're seeing right here. And there's just this idea, this is a kind of a classic idea, that we have registers, okay? And we have an ALU, right? And we can pull, these from this register bank is maybe what I should say. I can pull into some kind of immediate registers. There's these buses. Anytime you kind of see these fat arrows, you can think of that as a bus, meaning, remember the other day I mentioned a bus was basically more than just one wire. All right, if you had a register of data, it's basically saying I have 8 bits in this register, so this is really like an 8-bit wire, or 8 wires is really how you want to think about it, right? And so I have an ALU, and then the ALU outputs something into an output register, And then from there, I can basically pass that data back into the register bank to override one of the registers. Okay. Okay, so this is kind of like the fundamental 3 stages of any computer these days, or like a modern computer. Okay, we do fetch, we decode, and we execute. Okay, we fetch the next instruction. Okay, we decode it, and then we execute it. Okay, so fetch, decode, execute. Remember that, fetch, decode, execute. Okay, we fetch the next instruction. Think about it, right? When you're running, whether it's assembly, whether it is C++, whatever, right? I mean, you can kind of think of the same thing, right? You're just going from line to line, okay? Each one of those lines is some kind of combination of zeros and ones instruction, right? And those zeros and ones mean something. Okay, we talked a lot about how maybe 0, 0, 0, 1, 1 or something, maybe that meant add. Right, we talked about that when we were kind of getting into the assembly language stuff. Okay, and we actually looked at specific encodings. So your processor doesn't understand add, right? That's a mnemonic for us humans so that we can write assembly code a little bit easier. Okay, what happens is, you know, if we step back a few steps to here, right? The assembly language, right? Add R1, R2, R3 could be like a MIPS assembly instruction, right? That ultimately, the processor just sees a bunch of zeros and ones, maybe 32 zeros and ones, and says, all right, well, the first 5 zeros and ones are going to mean add. And it doesn't know what add is, but what it does see is that, hey, those zeros and ones, they go and they activate some circuitry in my machine and they deactivate some circuitry in my machine, okay? And we started to see that through that ALU that we talked about the other day. And we'll look at again today briefly. Okay, so that's kind of, you know, when we fetch, the decode portion is basically taking all those zeros and ones and letting those signals propagate, and they just naturally will activate and deactivate some circuitry. Okay, and then the execute is essentially, hey, what circuitry happens to be left remaining activated? Well, it's going to do its thing. If it's an ALU and it has the add activated, then it's going to add whatever data came out of that instruction. Okay, so these are some of the common pieces that you'll see in this fetch, decode, execute cycle, or this just typical processor design or data path design. You'll see ALU, right? We know what that is, the arithmetic logic unit. You'll see a PC. Okay, that stands for program counter. And the program counter is going to basically hold the address of the next instruction. Okay, so you'll see oftentimes that most of the time that PC just gets incremented by either 1 or 4, depending on if we're you know, talking about the address of the next word or the address of the next byte, where the in memory where the next instruction is going to be executed. So PC, you'll see both in this architecture and you'll see in the MIPS when we look at that, or when you compare it to what you've seen in Zybooks. You'll see memory, right? Every machine has some kind of access to memory. We typically think of that as RAM, right? You'll see a control unit. This is kind of a nebulous thing. You'll see control circuitry all over the place. Okay, so I kind of have here, looks like one box, the control unit, but in reality, there's control stuff just everywhere. You can almost think of it like a spider web of wires that are reaching out throughout your machine. Okay, we have a few specific registers here that are named. I don't know that I've seen these names in other places, but the idea you'll see in other places. We have the memory address register and the memory data register. Okay, so the memory address register is going to hold the address of the memory that you want to access. Okay, so remember, we have this huge memory. It could be 4 gigabytes of memory space. Okay, I want to access a certain row. So this MAR is going to maybe hold the address of the row that I want to access. Okay, so if I want to access memory, I have to put that address that I want to access in the MAR, and that's kind of the interface. Okay, the memory data register is kind of the data version of that, right? So if I want to write something to memory, I have to put it into this MDR. At least that's going to be the microarchitecture that we're working with today. If I want to read something from memory, it's going to get read and placed into this MDR directly. Okay. Now, again, this is going to be a little bit of a different microarchitecture. So try to look at this with fresh eyes. Don't try to compare this to the MIPS instructions that you're already familiar with, because they're not quite the same. Okay, so let's take a look. This is the IJVM data path for like their version 1. I think they call it the MIC 1. Okay, so just little, this is the symbol for micro. So you'll see that throughout, just to kind of shorten that word for us, microarchitecture. Okay, so this particular data path, all right, it contains 32-bit registers. Okay, so whenever you see all these little rectangles here, these are registers. Okay, we'll kind of unpack what some of these names mean. One of them, the PC, right? Program counter, memory data register, memory address register. Some of the rest of them we'll unpack as we keep going. All right. These are symbolic names, meaning that these names don't mean anything to the hardware. Remember, the hardware doesn't understand anything. Everything that has like letters and names and words is only for you and I, so that we can kind of make sense of what's going on with transistors underneath the surface, right? All the hardware sees is, hey, high and low voltages are flowing through, and it just follows basic physics at that point. Okay, so these are symbolic names. These registers are also only accessible to the microarchitecture. Okay, so typically resemble variable names found in the ISA. What that means is you don't necessarily have access to these registers in your assembly language. Okay, so I'm telling you, hey, these are registers that your processor is using, but you can't write a line of assembly that says, hey, move something into the PC register or the MDR register. Okay, this is stuff that only the microarchitecture is kind of managing based on the assembly code that it sees. Okay, and you'll see some examples on it. Hopefully that'll make sense a little bit. Okay, now this is really interesting, because what you'll see is this architecture is going to maybe feel a little bit, it might upset you a little bit, okay, because you might start to think, for multiple reasons it might upset you, but one of those reasons might be that you're starting to think, well, this isn't very efficient. Okay, it seems to be that we got to go through a few cycles just to do something that is seemingly basic, and that's true. We'll build on this a little bit. We'll get it a little bit more optimal, I will say. But just to take it for what it's worth right now, and just look at the structure of it for now, and try to just convince yourself that the things we're talking about in terms of how data flows through it makes sense to you. Okay, so what you see here is that most registers output to the B bus. Okay, so you can see this, we have this over here, this kind of grayish arrows. This is the B bus, okay? Notice the A bus right here. Okay, it's very small. And then notice the C bus right here. Okay, so let me kind of ask you a question right now. I'll give you like maybe a minute or so as a kind of a breakout. Let's say that you wanted to add the value, whatever was in PC, that register, to whatever was in SP, okay? How might you do that? What are maybe some of the steps that you see that you might need to take to do that? Can you do that in one kind of cycle? Can you do it in 2 or 3? I know we haven't unpacked that, but just given your limited knowledge and what you see, try to start reasoning about that a little bit. So grab a partner too, and see what you come up with.
Yeah.
All right. So let me ask you a question. So what did I say? I said add like PC to SP. Is that what I said? Can you get PC and SP into the ALU at the same time? Okay, so I see a no. What do you kind of think may need to happen? Say that again. Okay, and when I add it to 0, what's going to happen to it? Or what should I do? Okay, yeah, so you can basically see that the way this microarchitecture works, which again, you may think, oh, this is a little stupid, right? Or maybe you feel a little bit frustrated with it, but this is how it's set up. Is yeah, you basically have to take like SP or PC, doesn't matter, right? Take one of them. You got to take it through the ALU, add it to 0 essentially, right? And then bring it back to H. Okay, and then you can take the next one, whichever one we hadn't used, I think it was PC maybe. You bring that in there, and now you can add whatever's in H, which was the value in SP, to whatever's in PC, right? And then from there, you can output that, and you can save it in any one of these registers. Okay, so a little bit, right? It seems a little bit inefficient, but that's kind of what we're starting with, right? Now this is, if we look at this ALU, right, we're kind of opening this ALU up a little bit. And this is, you know, we talked about this last chapter. If you want more details on this, go look at one of the videos, and we maybe probably spend about 20 or 30 minutes just talking through this and really breaking down the wires. But over on the right, this is a 1-bit slice up here. And what we said was we can basically tile each of these slices to make, in this case, what you see is basically like an 8-bit ALU, right? It adds 2 8-bit numbers together, or it can and 2 8-bit numbers together, or 2 8-bit numbers together. So we are going to, well, in this particular implementation, we're working with 32-bit registers. So obviously this is going to be, this ALU is going to be a 32-bit register, or a 32-bit ALU. Okay, and that's actually what you'll be creating, I think, in project 3. Maybe it's 16, can't remember. I think it's 16. Okay, so over here you can see, you know, we have a number of input signals. We have F0, F1. This is passed directly through the decoder. Okay, so remember we had that fetch, decode, execute cycle. Okay, so at this point, we're kind of in the decode stage. We have the instruction, whatever 0s and 1s happen to be a part of this instruction. Okay. And we just pulling apart 2 of those 0s and 1s into this decoder, okay? And this decoder is going to pass out exactly 1 from these, 1 from these AND gates, right? 3 of them are going to pass 0s, 1 of them is going to be 1. And we basically showed how, let's say that we passed in 0, 0. All right, if we pass in 0, 0, then that means the inputs to this AND gate is going to be 1, 1, right? If we trace it up, that's going to activate this AND gate, right? All of these AND gates are going to be 0. So what's this AND gate being fed by? Well, it's being fed by just the logical AND of A and B. Okay, so if I pass in 0, 0 for F0, F1, I'm trying to do a logical AND. And we see that if we look over at this chart, you can see these are just some useful combinations of ALU signals. We can see over here, right? I mean, if we look 1, 2, 3, 4, 5, 6, there's 6 different inputs. And this is kind of the function, like what's the practical output of the circuit, what's it doing, right? So 6 inputs. So how many rows could we make this truth table if there's 6 inputs? Don't give me the exact number, give me the power of 2, right? 2 to the 6, right? Which is what, 64? So this truth table could be 64, right? So there's lots of things we could do. These are just the most common things, right? If you just want to pass, well, let's actually go look at our example. You'll see A00 for F0, F1, right? It's the only row here, and you can see that's the one that actually is doing A and B. Okay, so you can see we have an enable A and enable B, right? So if we enable A or B, it's just going to pass those values just as is. If we disable either of those, it's going to pass through 0 in place of those values, right? So if we pass in 1, 1, 1, 1, 1 on the A lines, but then we say enable A is 0, it's going to basically pass through a bunch of zeros instead. Okay. invert A and increment A. What can we do with those two? Those are two interesting ones, right? What can we do to a number by inverting it and adding 1 to it or incrementing it? 2's complement, right? So what you can see if we're kind of looking at this function here, notice here, if we want negative A, okay, well, I'm doing function 1, 1. If we look at past 1, 1 in, you can see that 1, 1 right here is going to activate this AND gate, which is the one that goes into our full adder. Okay, so 1, 1 is going into the adder circuitry. Okay. And you can see enable A is true, enable B is false. So whatever is on the B lines, it just says whatever, like I'm going to add 0 to whatever A was. Okay. So A is what it is, but then you can see we have this invert A and increment A are high. So that's basically what it'll invert it and add 1 to it, which will effectively give us the negation of that number. So pretty cool, right? We can actually do negation that way. Likewise, you'll see there is like a B minus A. So same concept, right? We got 1, 1 on these input lines. And then we have enable A, enable B. So we're going to pass A and B straight through, but you can see I'm going to basically negate A. So I'm really doing B plus negative A, or A, I guess negative A plus B, if you want to look at it that way. This just reads a little bit cleaner with less symbols. So you can see I can't invert B, okay, by the way that this microarchitecture is set up. So if I ever want to subtract a value, it has to be on the A input, if that makes sense. Okay. At least initially. Okay, so that is kind of the internals of the ALU we talked about in the previous lecture. And these are kind of some of the really nice functions. And this may be useful on your project too. If you want to test out your ALU, you can kind of pass through these various, combinations of inputs and see if it matches your expectation for the inputs for A and B that you gave it. Okay. So we've actually kind of already talked about this, right? What if we want to add 2 numbers? Well, we negate the enable A control signal to add B to 0, right? So basically we take one of these values out, right? We passed SP into B, and then we said, all right, with this ALU, let's disable A so that whatever was in here, whatever 1s and 0s happen to be in here, we just ignore them, right? So we're adding B to 0, which was basically adding SP to 0, and then we just pass it through. Okay, so allow the value to pass through the ALU and shifter into H. Okay, then we can add the new value, which we said was PC, into the ALU, and that will add it to the previously, what was held in SP, which is now H. Okay, so we can read. It's just kind of an assumption we're going to make. We can read and write the same register on the same clock cycle. It's not an assumption. It's just the way that this particular architecture works. Okay. So that's one thing, right? Because we typically think, hey, we can't have 2 values in the same wire, right? We can't have a 1 and a 0 on the same wire. But just imagine that these registers are set up so that, yes, they output, right? And the signal is going to propagate. And by the time that that signal is back in here, right, we're ready to gate it back in and basically overwrite. We basically, the value that we had in here, if we want to actually override it, we got it out and it's flowing through the circuit and doing what it needs to do. Okay, so you can read, write the same register on the same clock cycle if we want to. Okay, so here kind of just showing you, right, if you want to read, write, register SP. Okay, but we're going to put SP on the bus. Okay, we're going to disable ALU's left input. We're going to enable the increment signal. I guess we're adding 1 to it. I don't really explicitly say that, but that seems to be what's happening. We're going to enable the increment signal. Okay, so, and then we are going to store the result. Right, it's going to flow back through and we can store it right in SP. Okay, so again, the result of that was that we incremented SPY1 because we passed a 0 through on this side, right, by disabling the left input, that A, but then we did say 1. So we said 0 plus 1. And then that would be SP plus 1 as that left input. Okay. And this is possible because of the timing of the release and latch-in. okay, the timing of the register release and latching. Okay, so we're going to get a little bit in the circuit timings here. Maybe for you ECE, this is starting to feel a little bit more comfortable, right? We're starting to get like timing diagrams. You guys do timing diagrams and stuff like that, right? So this is maybe a little bit more, may feel a little bit more like you're getting into your zone here, though we won't go too deep into this. Okay, but this would be like a kind of a timing diagram for this particular architecture that we just looked at. Okay, so you can see I kind of have a cycle up and down. You can see it's not like a 50-50 duty cycle. If you've heard that phrase, 50-50 duty cycle means my clock is just high half the time and then it's low half the time, high half the time, low half the time. So this one's, you know, it looks like maybe, I don't know, 20, 80 or something like that. It just kind of gives us a little blip, which is fine. Doesn't really matter. Okay. But you can see basically what we're saying is our cycle 1 starts here, okay, on the falling edge. All right. And this first little delta of time, delta W, let me see if I can zoom in a little bit here. Okay. This delta W, this first little amount of time is when we set up the signals to drive data out of the registers and onto that B bus, for instance. Okay, so that takes some small amount of time for that data to flow out into those registers. Okay, and then the next small period of time is when we're driving H and the B, driving H in the B bus. So if we look back, right, we're kind of driving H down here, right, into the ALU. Okay, so this first little chunk of time, W and X, is basically we're just driving those two signals, right, into the ALU. Okay, and then it takes some time for those signals. It takes some time for those signals, right, to propagate through the ALU and the shifter. And we talked about the ALU being able to do, in this example, it can do add and subtract, right, if we do the 2's complement. It can do ands, ors, and nots. All right, so those are kind of the 4 general functions that we can do. But we also have a shifter down here. Okay, so if for whatever reason we want to do some bit shifting, if we want to do a quick multiplication of a power of 2 or a division by the power of 2, we can do that. Or if we just want to shift our bits for whatever reason, we can do that. So that's something I hadn't explicitly mentioned, but that is down there to add a little bit of extra functionality beyond those 4 basic functions that we can do with our ALU. Okay, so it takes some time for the data to then flow through the ALU, right? And depending on what 0s and 1s are being decoded for that ALU, it's going to add or and or whatever it's going to go through. Essentially, it's going to flow through all these, you know, Boolean gates here. Okay, it takes time. Okay, and then finally, after it makes it through the ALU and the shifter, propagation delay through that, it's going to propagate from the shifter back to the registers. Okay, so the idea is that it gets back to the registers at some point, right? Where, so basically we're saying, hey, the data has flown through the ALU and it's basically coming back up and, you know, it's sitting here banging at the door to the, to one of these registers. Let's say the stack pointer is what the SP stands for. So it's sitting there banging at the door, said, let me in, but that stack pointer register is not opening the door yet, okay, because it has a very specific time when it opens the door. Okay, so you can see that point is basically going to be at the rising edge. Okay, so registers loaded from C bus in memory on the rising edge of the clock. Okay, and this is the reason why we don't have a 50-50 duty cycle, right? Because remember what we said, well, if you're here, right? But what I kept saying is when we're looking at digital logic, the only time things happen are on the rising edge or the falling edge of that clock cycle. Nothing's really happening, right? If I have just like this up down clock cycle, right? I mean, it's always going to come down, but like this time, nothing's happening, right? No, I would say no changes are happening. All that's happening during this time is what you see here. Signals are just propagating. Okay. So basically, so if I kind of scroll down here, you can see this statement here, right? So the hardware design engineer must ensure that delta W plus delta X plus delta Y plus delta Z, that is all the time it takes for the signal to propagate, right, from getting out of the registers, flowing through the ALU and all the way back to the register, because that's kind of the full data path right there. The hardware engineers basically must ensure that that can happen, the worst case propagation delay through that, right? The absolute worst, longest time it could take is shorter than when the next rising edge occurs, because that's when, like I said, it's going to be the data, you know, from the results of that ALU is going to be sitting there banging at the door of that SP, but it's not opening, right? That SP is not opening its door to take in a new value until the next rising edge. Okay, and then it'll latch that in on the next rising edge. And then on the falling edge, which should come shortly after, as according to what we see here, that's when we can basically start a new cycle and we can, something else can be released out onto that B bus again. Okay. So, and that's why in this particular design, right, we don't have a 50-50 duty cycle, because imagine, right, if it was 50-50, then essentially that falling edge would probably come right about here, right? You can see if I'm just looking at these two, let's just start here, right? From this falling edge to this falling edge, about the middle point looks like maybe about right here, right? So basically, if we just did a 50-50 duty cycle for that clock, we would be latching in that data while the result was really still making its way through the ALU shifter, right? So our data is flowing through, it's going through the ALU, and all of a sudden up here, I'm saying, oh, cool, let me take in a new value for SP, but it's not there yet, okay? So let me pause right there. I'm not even gonna ask you any questions, but what I want you to do is take maybe a minute or two with a neighbor and just kind of talk through these propagation delays a little bit and some of the little design here, and see if you can just convince yourself that you generally understand the concepts that we're talking about here.
Yeah, because I was like,
All right. Any questions? Any questions? Follow up before we move forward. All good? Okay, so let's keep going. All right, so most of these registers are going to have, most registers in this particular microarchitecture are going to have two control signals. And this is true in general, microarchitectures, they have control signals, which basically tell them which ones can be released out into the bus. If you think about MIPS, remember we had like S0 through S9 or something, and then T0 or S0 through S6 and T0 through T9, something like that, right? We had like 16 or 17 registers spread through the temp and the save registers. So which one of those do we want to access, right? That's basically the idea. We can only access certain ones of those. Okay, so you can see over here, the B bus, each one of these registers that's connected to this B bus has a little kind of control signal coming in. Okay, and it's basically gonna, it should be set up so exactly one of these at most is high, right? Because we only want to put one register out onto the bus. If we put two registers, obviously we're gonna have some conflict. So that's kind of what's happening with the B bus. Now, those would most likely be implemented as, if you recall, tri-state buffers. Okay, remember a tri-state buffer has three states. It can be either be a 0 or 1, which is just passing in whatever its input was. If it's on, if that tri-state buffer is on, it just passes in whatever its input is. Okay, so in this case, right, if I turn on these tri-state buffers, it's going to pass out whatever the bits of PC happen to be. Okay, if that tri-state buffer is off, then it's basically going to take, like, if you think about it this way, it's going to take like a pair of scissors and it's going to cut that little bus entryway on, right? So it's basically going to leave this as like an open circuit. Okay, so one of these gate, if this tri-state buffer is on, right, PC is going to flow all of its zeros and ones out into this 32-bit bus. All the rest of them are just like stuck there. They basically don't have any access to that bus. Okay. All right, so let's take a look at some of these registers. All right, so at the very top, we have the MAR, the memory address register. Okay, this contains like 0, 1, 2, and this refers to consecutive words. Okay, so just to be clear, in this microarchitecture, the MAR is holding the word address, okay, which is not to be confused with the byte address. Okay, if we think about like, well, if we think about our typical memory, we said something like this. Maybe we'll draw a little picture here. Okay, we said we have something like this, right? Where we have, my memory kind of looks like this, right? And over here, we've got byte 0, byte 1, byte 2, byte 3, byte 4, 5, 6, and 7, 8, and so on and so forth. Yeah, it's an awesome 5 I drew up there. So we had always drawn like this. We said, all right, well, we kind of have address 0 over here, address 4, right, address 8, 12, and so on and so forth. Okay, those would be byte addresses. Okay, now what the MAR is holding is not byte addresses, but it's holding word addresses. Okay, so instead you would have 0, 1, 2, 3. Okay, so just to be clear, so essentially if you wanted to get the actual like the byte address from that, you just take that value in the MAR and you multiply it by 4, and then you're going to get the actual byte address, and we'll see why that's important in just a second. Okay, but that's important. Okay, so get my pointer back. Okay, when we put a value in the MAR, okay, again, that is basically the address that we want to read from memory. So I guess I need to delete some of these things. It's covering up what I want to talk about. Okay, all of these, you can see these kind of 4 hollow white arrows. These are all going to and from memory. Okay, so just imagine that even though it's not drawn, memory is somewhere out here. Okay, so if I want to read an address from memory, what's going to happen is I put that address in the MAR. Okay, that address gets passed along to my memory. Okay, and at some point later on, the result, right, I'm going to get me the word address 1000. right? At some point, that word, that data in memory is going to come back to me on in this register right here, the memory data register, okay, which I think we'll talk about in a later slide, but you know, talking about it now too, okay? So that's kind of what this MDR is, the memory data register, which is what's talking to our, I should have highlighted that one, but I didn't, okay? Likewise, right, if I want to write an address, then I have to fill the MAR and the MDR. So I fill the MAR with the address I want to write, and I fill the MDR with what I want to write at that address. And then those two values, you can see, have a pathway through these arrows, these two buses, to go directly to the memory. And it'll, you know, those, this will be used to basically decode the memory address. And then the MDR will have the value that actually gets overwritten there. Okay. The PC contains the byte, contains a byte address. PC is the program counter. Okay, so remember the MAR is the memory address register, and typically that's like, I'm typically pulling variables out in my program at this point, right? From memory. The PC is really just kind of holding the address of the next instruction we want to execute. Okay, so if you think about assembly, right, we've got one instruction followed by the next one, followed by the next one, followed by the next one. For the most part, these instructions are saved sequentially in memory. So somewhere those are saved, right? Memory address 0, address 4, address 8, so on and so forth. If they're 32-bit instructions. Okay, so again, this is the PC. And if I want to get the next instruction, you can see that that is connected to memory as well, right? I have the address, and then I'm gonna go and get that and bring it back. Okay. And that data can be read as a byte into the MBR. Okay, so the MBR is just a 1 byte version. It's very similar to the MDR. It's just if you only want to bring back a single byte. Okay. So you can see down here, if I put, maybe one kind of set of little instructions I can do for this data path, I can put the value 2 into PC. Okay. And then I can do a memory read, right? And then whatever byte happened to be, address 2, which we'll just call it byte 2, gets brought back into the MBR. Okay. So if I just want to read 1 byte, I can do it, yeah, but based on using the PC. For the MAR, right, I put the value 2 in the MAR. I'm going to read memory. I'm going to get bytes 8 through 11. Because remember, we said the MAR is holding a word address. So I just multiply it by 4 to get that base address of the byte I'm looking for. So 2 by 4 is 8. So 8, 9, 10, 11. Okay. So this is just simply to show this difference between the fact that the MAR works with word addresses and the PC works with byte addresses. Okay. And how does that work, right? Because we think about the MAR may have a word address, but in general, memory is byte addressable, right? If I pass like the number 1 in the MAR, let's say I pass the number 1 to memory, it's going to get me byte 1, not byte 4, not word 1, right? And so essentially what happens is whatever you put in the MAR, it gets shifted onto this 32-bit bus, right? So the bus that is actually going into, the memory. These bytes just get shifted by 2. You can see we just kind of hardwire the low bits to 0, right? And that effectively will multiply that word address by 4 to get the byte address, because the memory is only typically byte addressable. Okay, so that's essentially how that conversion is done. Okay. All right, so we just talked about the MBR a little bit, but here it is, right? So you can see smaller, it's only a single byte. I think we do 2 bytes as well. We'll get to that later on. But at this point, we can only do 1 byte. Basically retrieve a byte from memory. Okay. So the MBR can be represented as a 32 bits or 4 byte signed or unsigned byte, right? So let's say I get this 1 byte from memory. But if I want to do anything with this byte, right, I have to put it onto this bus. Well, the question is, what do I do? Because this was an 8-bit value and this bus is 32 bits, right? So what do I do with those high order 24 bits? Okay. Well, if it's unsigned value, I just toss a bunch of zeros out there, right? So 179 here, if you just add a bunch of zeros, it's still going to be 179. If it's a signed value, right? If I'm assuming that I'm working with a signed value, then the high order bits are all the same and are the same as the high order bit of byte 0 high order. So basically you can see here, if this is if this value has a 1 in that, highest order bits of the byte, then we're just going to sign extend that 1 to make sure that we keep that value as a negative value. Okay. Obviously, if it was 0, we would sign extend it to 0. Okay. Oh yeah. Okay. So you can see how there's 2 arrows here. So those 2 arrows, these 2 control signals on this MBR are to tell it whether to do signed or unsigned. Okay. So you guys probably, I don't know if we did this in any of the MIPS stuff that we did, but there are, if we look at the green card, for instance, there are unsigned versions of all the ads. I don't think we did anything with them or used them per se. Maybe you did in one of the little lab problems. But for the most part, I think we just assumed everything that we were doing, adding, subtracting numbers, was all signed by, so we could work with negatives. So if you were doing one of those like add instructions, it's a signed value, so it would basically activate maybe this left signal. Versus if you called an instruction that was like an add U, like an add unsigned, it's basically saying, oh, these zeros and 1, we're going to assume they're unsigned, so it just treats them a little bit differently. This is one of the places where that would come into effect in the actual microarchitecture, where it would say, hey, when you're putting this value onto the bus, go ahead and sign extend it, the zeros or the 1s, right? Versus the unsigned, if it was the unsigned signal, it would just always unconditionally add zeros there. Okay. Okay. So let's say that we want to read some memory. Okay, we've talked about this already, but I'll just have the slide for it here now. So it's going to take some time, right? We haven't really gotten into memory and memory hierarchy. We will, but reading memory is incredibly slow compared to how fast your processor is moving, right? You may be able to do something here in nanoseconds or fractions of nanoseconds, whereas going out, think about it, right? When I go out to read memory, is that memory on the same physical component as a CPU? No, it's not, right? Think about a motherboard. You got your processor here, and you got your memory maybe somewhere up here. It's a few inches away, maybe, right? That's like light years away in electrical speed. Okay, when we're talking nanoseconds. So it takes a while, right? We can crank through a lot of cycles typically. So in the first cycle, all we're really doing is we're loading the MAR and the PC. Okay, if we want to do a memory read, that is. All right, so we load the PC and the MAR. And the memory read, memory is read and returned in the MBR at the rising edge of the second cycle. Okay, so little caveat